Question 15 is another waves question, and you're presented with quite a lot of information at the start. It's really important to read through all of this carefully so you don't miss any details. So this is an application of something which is going to answer part A, which is the Doppler effect, where you get a change in frequency or wavelength of a wave due to the movement of a source of waves, or in this case, due to the movement of something the waves are reflecting from. So this is taking an idea that you would have looked at for proving that the universe is expanding and applying it to a slightly different situation, which you may or may not have seen. So the idea is the radar gun gives out the microwaves, they bounce, reflect off the car, and the microwaves return to the radar gun. And it tells you there's a change in frequency. Okay, so the name we've already said is the Doppler effect or Doppler shift. It doesn't allow redshift or blue shift. Maybe it might be slightly harsh to not allow blue shift. The main reason for that is this is not talking about visible light. Visible light can be redshifted or blue shifted towards the red or blue end of the visible spectrum. The microwaves are already outside that, so calling it redshift or blue shift is not really technically correct. So, how is the wavelength of the reflected microwaves different from the wavelength of the microwaves emitted by the radar gun? Well, if we're talking about our Doppler effect, then the source here, the car says is moving towards the police officer, it says up here. If the car is moving towards the police officer, then the waves, as they reflected off the car, are going to be squashed in the direction that the car is travelling, which will mean that the wavelength is shorter. Okay. It says ignore reference to speed or frequency altogether. This might be slightly confusing because it's talked about frequency shift, but whenever you have a frequency shift due to the Doppler effect, there has to be a wavelength shift that goes with it. And the reason for that is that the speed of the waves stays the same. So 15b part 2, the speed of the microwaves emitted by the radar gun is 300 millimeters per second. What is the speed of reflected microwaves? It is the same. Right? The reflection process doesn't change the speed. That only depends really on what medium, what material the wave is travelling through. Okay? And because of the equation that links frequency, speed, and wavelength together, if speed stays constant, wavelength decreases, then frequency is going to increase. So there's a tie-up there between frequency and wavelength that means they have to change together. Okay, so that's the first part of the question, which involves recall about the Doppler effect. And then the second part is interpreting some data. So what we've got then is a graph which tells us what the observed change in frequency of the microwaves is. Now, whenever you get presented with a graph, the first thing to look at is what is on the axes, okay? Because if you don't know what's on the axis of the graph, you're not going to be able to interpret the graph correctly. So, a car is travelling in an area where the speed limit is 70 kilometers per hour. The frequency of the microwaves emitted by the radar gun is 27 million kilohertz. The frequency of the reflected microwaves is 27 million and 4 kilohertz. The graph shows the relationship between the speed of the car and the observed change in frequency. So, because of this word change here, we know we're going to have to be calculating a difference between two frequencies. And the only two frequencies we've been given are these two up here. Okay, so is the car exceeding the speed limit? Use the information from the data given and the graph to explain your answer. So, using the information from the data given, we look at this and we go, okay, well, this is the information I've been given, and some information about the speed limit. I've got the speed limit and I've got the frequency shift. I need to change this frequency shift into a speed. So we do the difference between them to give us our change, and that gives us 4. And we go to our change in frequency axis, find the value of 4, and we read across and down, and we see that that pretty much lines up with 80 kilometers per hour. When you do this in the exam, mark it on the graph. Draw a horizontal line across from 4 till it meets the line on the graph, and then draw a vertical line down to show what you've done. Okay, then it's really clear that you've used the information from the graph. And then the only other thing we have to do say is yes, because the 80 kilometers an hour is faster than the 70 kilometer an hour speed limit. Okay. So, just looking at some of the stuff from the mark scheme, you could do a different approach, right? That approach that we've just talked about is finding out what speed the car is going at by looking at the frequency shift. You could go the other way, and you could say, okay, what frequency shift would I expect at 70 kilometers an hour, which is the speed limit? And you go up from 70 and across, and you should see the frequency shift is 3.5. And because that's less of a change than the observed frequency shift, which is 4, then yes, they must be speeding, because at the speed limit you'd only have a frequency shift of 3.5. To me, the first way makes a lot more sense. Okay, so 2 marks there for that. Now the last part is talking about a different car, and this time the key difference here is, well, we've got a different frequency shift. We've now gone down 2 kilohertz, and here it's asking directly for the speed and direction of the car. Show clearly how you work out your answer. 3 marks this time. Okay, so again, we're doing exactly the same things we've just done. Okay, we calculate the frequency shift, which is 2 kilohertz, and again, if you look on the mark scheme, it says there for 1 mark 2 kilohertz. It doesn't care about the sign, and the reason for that is there's only positive frequency shifts on our graph. It doesn't make any difference, all right? The way we tell the direction is by whether the frequency's got higher or lower. Okay? So we take our 2 kilohertz and we read on the graph that must be 40 kilometers an hour. So that's 2 out of the 3 marks. 1 mark for the working for 2 kilohertz, and 1 mark for showing that's 40 kilometers an hour. Again, draw the read off on the graph so it's really obvious what you've done, because then you are showing clearly how you've worked out your answer. And then the final mark here is for the direction, and we have to think back to what we started with here, which if the car is going away from us, then we'd expect the frequency to become lower, because the wavelength would get longer. Okay, so that's what's happened here. The frequency has got lower because the wavelength is longer, and so the car is moving away from us. There you go.